today's speaker. We have a very special guest again, who embodies very well the topic of this colloquium, which is interdisciplinarity. He comes from computer science. However, he took upon a very intersectional topic between technology and law, being IT security and data privacy. He focuses on data security and network security, with a focus on the user in context of social media and large systems. I welcome Professor for IT Security at KIT and Honorary Professor for Data Network Security at TU Dresden and PI at the German Competence Center for IT Security, Kassel, Professor Dr. Thorsten Struve, and I will give to him now.
That's very kind. I try to stay in front of the camera. We just had the discussion that I walk around during presentations. So if you don't see me, I'm not gone. It's just that I'm walking around. Another quick thing. So, well, first of all, thanks a lot for the invitation and also for the nice introduction. Another quick thing. Usually, I tend to talk a little bit longer at my slides than I'm planning. So if you have questions, it's going to make a lot of sense to ask right away, despite the fact that then you have to disclose who you are to YouTube. Because otherwise it may so happen that at the end of the presentation there will be not much time left, at least for the scheduled 1 hour. But I'll try to make do with what we have. All right, so thanks again for the invitation. I was invited to say a few things with regards to privacy considerations in academic research as part of this interdisciplinary colloquium. And I've been thinking quite a lot, so I didn't really have like a presentation available that I could use. I had a very old presentation on ethics in research, but then I realized that maybe you know more about ethics than I do, and hence I decided that that maybe it's less useful if I go down that path. So instead, I tried to figure out what our experiences are that could be useful to you, and I believe that. A lot of the work that we're doing at the moment could actually be quite interesting, and that goes in the direction of anonymization or showing the boundaries of how little anonymization actually works. But let's get started. So we're talking about privacy in the context of academic research. And then, of course, if we think about the scenario of academic research, we have our scholars here in the middle. And usually then a lot of people all around the world, sometimes in Karlsruhe or wherever you're located, sometimes somewhere on the web. And what we do in order to do the research then is that we collect data. And one way of collecting data is that we crawl their web pages, or we ask them to access their web pages and get information about them. Or very often in the past, we've been building certain kind of applications that they would install in their computers or in their browsers. Now we install or we prepare applications for mobile phones that then people can install in their mobile phones. Then we can follow what they're doing. Sometimes we go about doing questionnaires and ask the people directly, or maybe, for instance, in one of our more recent studies, we're actually setting up an entire environment where then we're collecting information about how people are doing certain things or behaving and moving. And that, of course, leaves us with a lot of data. And that then, of course, primarily we're interested in, we want to investigate because we have a research question. But very often we also want to share it with others. And this is where things get a little bit more complicated. Now, if we think about different means of processing and data sharing, then very often we have 3 different types of models. And the model here indicated at the top would be what we usually want to do, or what we usually think would be the easiest to do. And that would be that, looking from the left to the right, we would collect the data from certain individuals that then, of course, is personally identifiable information. We'll look at what that means a little bit later. We have the data in some kind of a database, then we do some analyses, and then after we do our analysis, we also maybe want to publish it so that other researchers can work on the data as well. And for that purpose, very often we do something that you cannot see what I'm pointing at because I'm blurred. But here on the right-hand side, we do something that then we call anonymization or protection or something, so that then we actually can put data online, and we hope that everything is fine in that case. Suffice to say that usually not everything is fine in that case, and that's also one of the reasons why now in more recent years there have been 2 other models that have arisen. One would be like in the middle, the aggregate publication, where, for instance, the idea is that, again, we're collecting the data from the individuals, and then somewhere along the way, we're creating aggregates. So, for instance, we're training machine learning models, or we're extracting statistics, and then we publish the statistics or the machine learning models, hoping that the data cannot be extracted from those statistics, and that we don't really disclose any information about our individuals from the study in the first place. Or something, again, that is becoming more common, at least in computer science, is that we provide something that we call queryable access. So where then at the bottom here, we're collecting data, we keep the data in our databases, we also do our own analyses, and then we have some kind of a query mechanism, like if you wish, some kind of a database where then external researchers can send queries and receive answers. For instance, what is the average height of the people here in the room? And then there would be an answer to that query, so that then the researchers can, for instance, reproduce our research. I'm mainly going to focus at the first part here, because this, of course, is what we're most driven to do, because at the moment, or maybe for the last 8 to 10 years, it has been very fashionable to publish data sets. First of all, because it gives you citations, but secondly, of course, also because it provides other people to do research on the data that you've been collecting, so you don't collect it only for yourselves, but also for others. But then, of course, we have to figure out how can we publish that data. Maybe before looking into the ways that we can publish such kind of data, the first question could be what could possibly go wrong, and I always like to discuss this with my students. I have a couple of examples that I like a lot. So, for instance, of course, there's applications that you can install and that then you use for certain purposes. For instance, there's a cycle tracker application that you can get for free if your employer pays. And then what happens is that your employer gets access about your personal information that then can be used by your employer for certain purposes. Interestingly enough, this application has been in the news not because maybe the business model in the first place is a little bit strange, but because they were sending data to China, and of course that is something that you cannot do. So then they changed this, so they installed some kind of privacy enhancement technologies, so that then the data remains in the United States and Europe, and then suddenly apparently it's fine. Not sure, but anyways. Of course, we can talk about Facebook, but we don't need to do that at great depth, because we know that the core competence of Mark Zuckerberg is to say, I'm sorry. But maybe there can be others. So maybe we could think about Google. Google is one of the large online or digital companies. So we would think that they know how privacy works. And it turns out that, for instance, they had a large court case because they were offering Chrome, or they are offering, I think it's been sold now, but it's in the process of being sold. They have been offering Chrome as a browser, and in Chrome there was an incognito mode that made people believe that what they're doing remains private, which of course it doesn't. And in the context of Chrome, they have also been talking about the Google Privacy Sandbox, where they were saying that you can then use Chrome and nobody knows what you're doing. You will have privacy online. I did a quick Scholar search, and it turns out that 2 weeks ago, there have been 231 results in Google Scholar about how the Google Privacy Sandbox does not protect your privacy. So that's essentially the research that people are doing. Maybe thinking about Facebook or Google, it's obvious that privacy is not so much of an issue. And sometimes I'm thinking, who should be able to do it well? And then you think something like, maybe the military, right? So you would say that the military should be able to protect their private information because maybe then human lives are at stake. Turns out that I don't know if you've heard about that. That, for instance, some of the some of the American soldiers have been using fitness trackers and publishing the data about their runs, their regular runs, and the information then, of course, aggregated, disclosed the place of some secret army bases. Now you can say, okay, so this is like this article has been a long time ago, so maybe, of course, the American military would learn. Turns out that this is like 2 years ago, 3 years ago, that the American military hasn't learned so much, because then broker sales of US military personnel data overseas have been stirring national security fears, because in essence what happened is that people using apps on mobile phones and using location services in mobile phones have led to the situation where the apps have been sharing the location with data brokers, and data brokers have been selling this data that then, of course, can be collected. But okay, maybe the military has lots of people to lose. Thinking about other instances that should be able to do it properly, for instance, the secret intelligence agencies, CIA and NSA, it turns out they also don't really know how to do it well, because as a matter of fact, the same leak happened that people have been sharing their location. And then in the article, I recommend reading it. It's quite nice. The journalists have been pretending that they would be interested to buy location data from data brokers. And the data brokers happily showed them in real time where NSA agents have been around the world, in essence. Now you could still say this was like in 2022, maybe by now we have learned something. This is now from November 2025, and you may have heard of that, the data broker files. So this thing is still happening. So suffice to say maybe that privacy is somehow an issue, and not only in academic research, but it turns out that we don't really, maybe as a society or also as technicians, we don't really know how to deal with data to make sure that privacy is actually respected. Okay, but let's have a look a little bit deeper at the problem that we have at hand. So maybe first of all, a very quick computer scientist definition of personally identifiable data. So personally identifiable data, in our perspective in computer science, is data that refer directly or indirectly to an individual or their characteristics. So let's say we have data about a certain person, Bob, for instance. The data may contain certain information like that Bob is a union member, and maybe the data has been published or edited from somebody's mobile phone, where maybe the mobile phone or the IP address is attached to it. So we have certain references to the person who has actually been creating this data and to whom this data actually belongs or refers. Now, personally identifiable information in itself is probably not so much of a problem. However, as soon as we think about adversaries that want to learn something about individuals, we're talking about linking attacks, where essentially the idea is that somebody may be able or may want to discover the connection between items of interest, where then the items of interest can be anything that we see here, right? So for instance, an attribute of a certain person, or the identity of a certain person, or where a certain person is, and so on. And this very often may happen by an observation that somebody has and auxiliary knowledge. So for instance, knowing that there's a mobile phone at this place right now, and at the same time knowing that I'm giving a presentation here, then essentially linking these two information together and then learning that probably it's my mobile phone which is here. All right. Now, that was essentially a technical view from a computer science scientist perspective, thinking about what normal people will expect if we tell them we will collect your data and we will do something with your data. The normal assumptions or expectations of users usually is as follows. So for years with IT security and crypto, we have taught the people that what happens is that you can essentially take a message, your email, whatever, your signal message, and you can encrypt it, and then what an adversary that is observing the message outside of the trusted domains of the users sees is like white noise, right? So we have trusted domains. Alice resides in a trusted domain, which is her mobile phone, for instance, or a computer. Bob resides in a trusted domain, same thing. They can use crypto algorithms to decrypt and encrypt and decrypt maybe. But in the meantime, outside of the trusted domain, everything looks like white noise. So then if we think about data protection or anonymity, what people are thinking about is more or less the same, right? So they know that, of course, we have a situation where there are several users. They also know that there is, the data is going to be collected at some stage, and they also know that others will be able to look at this data. However, what they believe is that the same thing is happening, so that what they're sending to the service is essentially invisible outside of the trusted domain, and that anybody else cannot make any inference about whatever they're doing, so that there's an absence of linkability, if you wish. And unfortunately, of course, this is not correct. So if we look at the model or at what data protection or privacy can actually offer, then maybe we can say something like, okay, maybe we can have something like private processing, where private processing would be essentially processing of information while identification of the data or attribute disclosure are prevented. So, and if data is shared, it's shared at reduced detail. So Alice, Bob, and Charlie here would know that, would not know, but what happens is that they would share certain information with a certain service, but others that are getting access to this data would only see something that does not disclose anything about any of the individuals. Of course, we can already see that there's some kind of a privacy utility trade-off, right? So of course, we see that suddenly here there's no white noise. There is some kind of an information. And the amount to which this is not white noise, but this is actually useful, of course, increases the utility, but at the same time, it comes at the cost of privacy. So the more information we leave in the data, the more detail is retained, the less privacy, but usually then also the more utility we have. Now, sometimes we have people from computer science who are saying we can achieve privacy. It's super simple. What we can do is we can encrypt the inputs, and then maybe we can even process the data in an encrypted domain or a trusted domain. So in essence, extending the trusted domain from only the device of the user to the device that is actually processing the data. And then, of course, that is essentially taking the input data and generating this output. That, of course, provides a certain kind of a protection for certain, in face of certain adversaries, but then we still have the output. Usually what we call this is input privacy, because essentially the inputs are encrypted. So an adversary who's listening in on the channel, for instance, cannot do anything with the data. Potentially even the server provider cannot do anything with the data. So the inputs remain protected. However, the situation with regards to the output and the privacy utility trade-off remains the same. And if we think about this second part, where we actually have to make sure that information about Alice, Bob, and Charlie are not disclosed, this is output privacy. So this is something where we have to do something on top. And essentially that is the idea, where we want to prevent any disclosure outside of the trusted domain, because worst best case, the trusted domain ends here and the rest is on the internet in essence. All right. Now, what exactly are the threats that people can have to fear if we think about publication of certain information that contains data about individuals? Usually, again, in computer science, what we do is that we like to put things into small drawers, and we usually distinguish between two types of threats, where the first threat is identity disclosure, and the second, the disclosure of attributes. Now, what does it mean? It's not super surprising, but if we think about identity disclosure, then the threat would be that we're able to identify an individual. For instance, if we have a large data set containing plenty of records, if we then know, so this record refers to Bob, for instance, then we have an identity disclosure. Same can be that we can link an identity to an observation. So for instance, if we think about anonymization systems like Tor, if you don't use Tor, but you send an email or you send any message over the internet, then of course the observation of the message contains the IP address from where you sent it, so you can directly link the information to a certain identity. The second here is disclosure of attributes, and that's essentially correspondingly the idea that we thought before. So maybe we already know that a record exists and that the record is referring to or corresponds to Bob. But there's certain information in the record that we haven't known before, and we learned something new about Bob that Bob maybe didn't want to share. For instance, that he's a union member, that he has certain diseases or whatever. For the rest of the talk, I will be talking about identity disclosures and trying to prevent identity disclosure. I just would like to raise your attention quickly to the fact that attribute disclosure does not necessitate identifying individual records. So for instance, if you have a database where you're not able to single out certain individuals, but you have certain groups that share certain properties, certain attributes, and you know that an individual is part of the group, then of course you already learned that this individual also has this attribute, so you don't even need to identify someone. But for the moment, let's try to figure out if we can deal with identity disclosure. Now, again, putting things into drawers as computer scientists, how do we actually link individuals to data? And of course, if I would ask around, so there's not a super big audience here in presence, so I'm not going to ask around, but usually if I talk to my students, then I ask around, then what happens is that people directly have the idea of explicit identifiers. So also when you collect your data, you have a questionnaire, you write down, this is Thorsten Strufe, and these are his answers. So you have like an explicit identifier, right? And explicit identifiers can be many different things. Let me not disclose too quickly. But of course, it can be something like Alice and Bob being denoted by A and B, or it can be personal names, Franziska, Thorsten, whatever. By the way, personal names are not super identified. So Thorsten Strufe, unfortunately, is. There's only 2 Thorsten Strufes around the world. But very often names are not so identifying. So as a matter of fact, in many cases, you could actually keep the name and you would have like a K anonymous set of, depending on the name, quite a few people. Maybe better identifying are things like service numbers, if somebody has been serving in the military or whatever. Portrait pictures are usually quite identifying. I mean, at the end, it's just like a number of pixels. So it's just like a representation of an identifier. Or of course, the best possible identifier would be in a DNA, where we obviously with the identifier already have attribute disclosure on top, because of course from the DNA we could not only learn this is data that corresponds to Thorsten, but it's also data that maybe contains certain diseases. By the way, also regarding the family of Thorsten and so on. So these are usually the identifiers that in academic research we have to deal with directly, and that we also think about a lot. However, unfortunately, these are not the only things which are identifying people. So, for instance, less obvious, there are also technical pseudonyms. So, for instance, you have cookies, IP addresses, or certain handles which also directly identify the people. However, we don't commonly think about that. Or maybe sometimes we have we do a lot of work with web activities, and in the referrers, very often you have direct names or direct identifiers written in the referrer, technical pseudonyms. Maybe again, a little bit less obvious, I guess, that everybody has heard about Latanya Sweeney's paper. The fact that if you take the American population, you can identify, I think it was 87% of the American population. If you take together, sorry for walking out of the picture, if you take together the date of birth, the gender, and the postal code. So this tuple alone is sufficient to identify a large number of people in the population. Usually we call these quasi-identifiers because each of these attributes does not identify someone, but in combination they do. Same thing happens for browser fingerprints. If you delete your cookies, but you have a very specific browser, then the information, for instance, which kind of screen resolution you have and which fonts you have installed, does identify you in this sense as a browser fingerprint. Again, maybe less obvious, or maybe for you it's not, but for computer scientists, usually again less obvious is something like biometrics. So very often biometrics are perfectly identifying. So of course we know fingerprints. I mean, everybody knows Sherlock Holmes. But then there's also iris scans. Maybe you've seen Illuminati, the video. As a matter of fact, there's also things like biometrics like heartbeats, the specific pattern that the heart beats is identifying individuals. Limb proportions are identifying people. The posture is identifying biometric, or for instance, we're also working with brain waves, so EEG. EEG data is perfectly identifying individuals, and you can collect this data. If you collect it over a certain amount of time, you can perfectly identify from whom this data stems. You may be saying that if we do step aside, if we do a realistic risk assessment, you may be saying that, for instance, heartbeat or something, maybe it's identifying someone. But how do I know? I mean, somebody would have to go to the hospital and get the heartbeat taken or whatever. But I would like to remind you that many of us are wearing fitness trackers now, and fitness trackers capture the heartbeat all of the time, and they share it with American companies. So here we go. By the way, also data leaks are happening all of the time, so well, very frequently. So this is a second, essentially, path where the data could become available. Now, these are still on the more obvious side. And these are maybe in most cases also NIMs that are explicit. So we think about this. If we collect data, then we think, okay, so this is something that we have to take care of, and that we can try to hide in some sense, to anonymize data. Unfortunately, even the content of studies. So if we're collecting information as part of the study, not as part of the questionnaire about the demographics, but as part of the questionnaire. Or the measurement studies very often is also identifying. So I don't know, I guess that I'm probably the oldest person. I'm definitely the oldest person in the room. But some of you may recall the sentence, and if you read the sentence, then some of you may know German and German politicians. And just by the way that the sentence is written, some of you are able to identify who it was. It was a person who was Prime Minister President von Bayern. Edmund Stoiber, maybe I'm really getting to. Anyways, so just by the way that somebody's talking, very often you can identify them. Or taking sequences of actions. And in some of our research, we have shown that, for instance, if we take a sequence of activities on the web, if I just know not even the specific article where you're going, but the web page and the category of information that you're accessing together with timing information. So 7 o'clock in the morning, somebody's going to Spiegel on, sorry, 10 o'clock in the morning, somebody's going to Spiegel Online, reading 2 articles on Spiegel Online, switching over to GMX, and then reading 2 articles on Zeit Online. Such kind of patterns are highly identifying. So there's studies that show that if you don't know who the person is, but you know essentially 3 or 4 web pages that a certain person visited during a certain amount of time, and you get access to browser tracking data, then you can find perfectly find the person from whom this data the person who has created this data. At the moment, we are doing a study where we show that even if you delete your cookies, so that let's say every time that you stop your browsing session and you delete your cookies, so you really only have each of the single browsing sessions themselves, that the characteristic of how you're browsing the web is still identifying. So your timing behavior and so spatial temporal behavior on the web is identifying you, so that we can link browsing sessions despite the fact that we don't have the cookies. Something else that has been also in the news is that the way that we're walking is identifying. You know that there's a large Asian country that is selling lots of hardware, and some of the hardware is video cameras, and in some of the video cameras there's functionality installed that you can identify people based on the way that they're walking, gait-based identification. The way that we're moving through the global space or through the geographical space, of course, also highly identifying. I mean, there's not super surprising if you know that there's a person who's leaving City Park in the morning and going to Fasanengarten every day, and then going back home or going back the other direction at night. It's not super surprising that you can identify who this person is. Exactly. And it turns out that anonymizing such kind of information, first of all, when we do studies, we don't really think about that. And secondly, doing effectively anonymizing such kind of data is extremely difficult, because I mean, if you, for instance, think about location data, very often what we try to do is we try to aggregate some information and then add some noise. But for trajectories, for instance, it's not really quite clear what noise does, right? So I mean, if you would take this point and you would move it here, then for an adversary, it's going to be obvious that you didn't take this path, but for them, it's quite obvious then how to essentially reconstruct the original trajectory. Or if we think about the way that people are walking, if there we would be adding noise, we'll have a study showing what happens. But then, of course, very quickly, the movement doesn't even look like a human anymore. So that then the utility, of course, is broken quickly. All right. By the way, again, if there's questions, I don't know if I don't think that anybody has been asking questions so far, but please go ahead, because otherwise I will. There's a question.
Actually, you have a
Go
question.
ahead.
Because I'm working with electrical drums.
Yes. Yeah.
And since you said that a lot of people are wearing their smartwatches and so on, I mean, there are some that also take your ECG, but that you have to do actively, or at least I don't know how it could be differently. So what you were referring to is probably the heart rate that is collected. So just
Garmin, there's a big company that is selling smartwatches. Well, so in that case, as a matter of fact, you have to actually start the collection of ECG. But for instance, there's another big company that has been bought by Google at some stage, and it has 6 digits, 6 letters in the name. They're collecting ECG all of the time. And they're essentially just storing it to where they can store it. So in that case, later on, the data is essentially available. And I mean, also, if you think about a very big, apparently Swiss watchmaker, they're saying that if you want to use this service, then you have to have like 2-factor authentication, and you have to protect your account better and so on. That doesn't change anything with regards to the fact that their databases get leaked every now and then, right? So some people break into their databases and the data suddenly becomes public. Makes things more complicated for you.
Your account that you have for the brand of the smartwatch, let's say, and then already it is identified, I guess.
There it's already identified in any case, right? Because they know you have an account. Yeah. So I think for me the more problematic situation is, I mean, if I have the watch and I turn this on, then I'm willingly sharing this information with this company, right? And then I cannot say, oh, but I didn't know. I mean, of course, people do that, but from my perspective, that is a strange kind of an argument. However, what happens is that this data leaks, or that this data is published, like the Strava data earlier, for instance. And then suddenly other parties get access to this information that you and I did not have a contract with, and or that agreed with that we allow them to process our data.
So
and then
basically, the problem is what comes after. So for me, for example, if I'm collecting my ECG and it's not leaked anywhere, in that moment it's fine. But as soon as it gets out there, basically, my personal data is somewhere where I don't want it to be, and I can't do anything about it.
If there's secondary kind of use of the data later on. I mean, maybe if my late father actually at some stage bought a smartwatch, and even in that case, we can argue that maybe that was already some kind of abuse because he didn't have any understanding of what was happening. He just saw that there's a step counter and that the watch was counting in the heart rate. But he didn't have any understanding that the data was sent to servers in the background or whatever. So there maybe the situation is already problematic in that regard. But I mean, for you and me, we would say, okay, you know what happens.
Yeah.
But then there can be secondary use of the data, which can also be a problem. Yeah, right, no worries. Okay. Okay, so we're talking about output privacy. And so first of all, now we have understood how we can link information to certain individuals, so how identity disclosure can happen. Now let's think about the question how we can prevent identity disclosure. And so there's also sometimes, very often, last week I was in Berlin for the Datenschutzkonferenz, where I heard many people say that it's not clear what anonymous means. And for me, that is not super strange. So the fact is strange because it's not super difficult. For a computer scientist, data is anonymous. Data is anonymous if it cannot be linked to any individual, then it's anonymous. Otherwise, if it can be linked to an individual, it's not anonymous. It can be pseudonymous if I have removed Thorsten Strufe as the handle, then it's maybe pseudonymous, but it's not anonymous. And if there's a chance to reconnect the data to an individual, it's not anonymous. So the data isn't anonymous in that case. That was a question.
We have a question from online.
Yes.
So the question, is there a difference between qualitative and quantitative data? If I use quantitative data and such methods like K anonymity, T closeness, and so on, will I not lose the individual in the anonymity of the group if the group is large enough?
Well, I mean, here's the thing that in the case of K, maybe I think I have, I will not reach that slide. But I have a slide about K-anonymity. The problem with K-anonymity is that in K-anonymity, we always make very specific assumptions about the knowledge of the adversary. So we say the adversary knows certain quasi-identifiers, and then according to those quasi-identifiers, I make my database K-anonymous, for instance, or L-diverse, whatever. And under those assumptions, then the adversary does not learn, in the case of L-diversity, does not learn certain things above a certain threshold. In the case of K-anonymity, it's already the case, what I was mentioning earlier, that if we have a group that shares all of the quasi-identifiers, so it's K-anonymous, but it also shares the sensitive attribute, then we learn that if I know that Thorsten is in this group, we learn that Thorsten has the sensitive attribute. So, despite the fact that the data is anonymous and I cannot perform identity disclosure attacks on the data, or I can perform attacks, but I cannot successfully disclose the identity of individuals, attributes are leaked. And beyond that fact, the problem is that with K-anonymity and the entire set of solutions that we always have to make assumptions about what the adversary knows. And in reality, that is very difficult because, I mean, what information does the adversary have at hand? Can the adversary only look at the phone book, or can the adversary also, I don't know, crawl the internet? So it's very difficult to define properly what information the adversary has. So despite the fact, again, that in the case of K-anonymity, identity disclosure may be prevented, attribute disclosure is not. I hope that answers the question. Although I'm not sure. Maybe it did. Okay, so here we said that data is anonymous if it cannot be linked to any individual. And the consequence, of course, is that if we think about anonymization has to be a one-way function. So from a computer science or mathematical perspective, a one-way function is a function where I can take an input. It creates an output that looks somewhat random or like random. And if I have this random looking output, I cannot invert the function. So I cannot learn which kind of input the data has or is corresponding to. And we'll realize in a moment that that is quite important if we think about anonymization. Now, there have been plenty of anonymization attempts to reduce information that allows the linking to individuals. And as a matter of fact, I'm pretty sure that so after 25 years of research in the field, I would say that that none of them works perfectly or effectively. So even if we say that we have data and that we anonymize data very often or very, very rarely is truly anonymous. So again, thinking about what anonymity means and the fact that maybe you want anonymity to get out of the GDPR. In most cases, data that you anonymize is not really truly anonymous. There have been different approaches that have been suggested, and we'll look at a few in a minute. But unfortunately, most of them are ad hoc. So people have been saying, oh, look, I do this transformation, and then afterwards it's anonymous. For instance, I train a machine learning model, AI, or I aggregate the data, and then everything is fine. So nothing can happen. And unfortunately, we haven't been vetting such kind of claims very well for a long time. So unfortunately, many people believe that this is actually correct. Then there's a second type of an approach, which we call the syntactic anonymization. This is, for instance, k-anonymity, L-diversity. So if we achieve k-anonymity or L-diversity, we call these mechanisms that achieve that syntactic mechanisms, because what they do is they take data, they do something to the data, they, for instance, generalize data, they suppress information, and they output data. And then the data itself has a certain property, for instance, it's k-anonymous or diverse and so on. Unfortunately, syntactic approaches, as I was just mentioning, first of all, they are very, very bad at preventing attribute disclosure. And secondly, they make very strong assumptions about the adversary. They say, I know what the adversary knows, and that can be an issue. Finally, I wanted to introduce that, but I will not have the time for that. There are semantic approaches, for instance, differential privacy, where the idea is that essentially you execute an operator. For instance, I was mentioning earlier, we can calculate the average height of the people in the room. So we calculate this height, then we add noise to the output of this operator, and we make the operator itself or the function itself secure or privacy preserving. And this is essentially the only type of approaches. So there's many different types of differential privacy, but there's the only type of approaches where we can really give guarantees. So independent of what the adversary knows, we can guarantee that there's no more leakage than a certain amount, for instance. And now you may ask, that's strange because there are so many people who have been claiming that they've been anonymizing data, and so many people are selling data saying it's purely anonymous. That's a bit strange, right? And I think the reason is that when we look at many papers that have been published, but also industry solutions that I've seen when talking, for instance, to data protection authorities, what happens is that somebody comes and they say, look, there's some data and I can attack the data. I can identify someone. And for instance, I can identify the face of someone. And then the second step is, okay, so then we remove the obviously linking information. So for instance, they slightly modify the face. And then they say, look, if I now do the same thing that I did before, it doesn't work anymore. So the data is anonymous. And this is usually how, or it has been for a very long time, how anonymity or anonymization approaches have been shown to work. And you may think that this is a joke, but it's not. There's one example that motivated us in our research for quite some time. That is essentially a university in the United States that published in 2020 a system called Forks, where they were saying that they can anonymize images, and you can see here on the left always the original image and on the right the cloaked image. And you will see that you're surprised that this is supposedly anonymized. Yet they made it into Gizmodo. They also made it into the New York Times. They also made it into DiTraRe. And by the way, so the first headline is, this algorithm might make facial recognition obsolete. So facial recognition is not going to work in the future at all anymore. Interestingly enough, the algorithm also made it into Wikipedia, where it's claimed to be perfect in the sense that it's anonymizing data or anonymizing faces. And now you may be saying this, I mean, the way that the person is presenting this here, this seems to be super stupid. And I agree. I mean, the way that I'm presenting it is super stupid. However, it's not always obvious. So privacy, technical privacy is a field that hasn't been researched properly for a very long time, especially when it comes to biometric data. So even Schneier on security, some people may know Schneier. Bruce Schneier is a person who is much smarter and knows much more about security than I do. And this person was essentially tricked into believing that this face is anonymous. So surprises. So let's just have a look and put a little bit of scrutiny to these claims. And I have I think four or five smaller studies that we've done, and some things which I've been stealing from good colleagues. When you talk to data protection authorities, very often what they hear is that you just have to hash the data. So I was mentioning earlier, hashes are one-way functions. They take an input, they make the input look rather random as an output, so that you cannot take the output and invert it back to the input. Hash functions also work the way that the same input always leads to the exact same output. And then the rationale is here that, okay, you take the identifier or identifying information, you use a one-way function, a hash, for instance, and then you output a pseudonym, and this pseudonym is uninvertible because you cannot invert hashes. And hence, very often then the claim is that the data is anonymous. Raptor, for instance, is saying that cookies are already hashed values because they're randomized, and hence data that is identified by cookies is anonymous data. So I think we can directly agree that this is complete bogus nonsense, but in any case. Other people have been saying in industry, we also may rely on third-party service providers to do things like take a user-level information, anonymize it through hashing. A hashed email address might look something like this, and match it against other information. And then, of course, you may think, okay, so if I take a hash function, if I take your email address, I put it through a hash function, it looks something like this the first time, the second time, the third time, every time. So in essence, you just have a perfect pseudonym that is perfectly identifying an individual. It's true you cannot invert it because hash functions are built in a way that you cannot take the output and invert it back to the input. However, there are not so many email addresses, so computers can easily try all of the email addresses, and since the output for the same input is always going to be the same, it's then easy to essentially enumerate all of the potential inputs, and then you will get the same output, and you can again link this. Interestingly enough, people are saying hashed email addresses cannot be decrypted. It's a correct statement because you cannot, it's not encrypted, it's hashed. But of course, it's nonsense because if you take my email address twice, it leads to the same hash value. Funny enough, there are certain application programming interfaces in this case, for instance, for Facebook, and they're requiring you to hash certain values. For instance, if you hash gender, it is required that you hash the gender, and you are supposed to take M for male or F for female. I mean, it's total complete bullshit because I mean, of course, it's always the same, so you may just as well ignore them. You could do hashing if in a more secure way, if you would always add a random value to the input. If we store passwords, for instance, that's what we do. And we call that sorting of hashes. Then at least if you use different salts, the same input will lead to different outputs. So for instance, your email address at Google would lead to different hash than your email address at Facebook, for instance. Interestingly enough, here's a screenshot from a web page saying email addresses should be hashed using SHA-256, so that's one hash function without sorting. So you should not do that because otherwise it will not look the same. And by the way, these are statements from Adobe and Meta, and you would think that these are companies that should know better, but apparently they don't. All right, so hashing. Anonymizations that take one hashing, despite the fact that industry very, very often claims that hashing would have any sensible use in the context of anonymization, it doesn't do anything. The second attempt, let's look at something that we've seen quite a lot. For instance, just use technology that humans don't understand. So I don't know, again, I'm probably a little bit older than others here, but you may recall that at Berliner Südkreuz at some stage there were video cameras, and then people were saying, it's not really great because, I mean, it's a public place and video cameras are not really great. However, there was a very well-known German minister at the time, or secretary at the time, that was saying, but security is so important, or safety is so important. So we just use something else, we just use depth cameras. So then suddenly everything is good. I mean, you don't recognize this person, right? So then of course the data is anonymous. A little later, we got a call that where the BMBF was asking us to check if this claim was correct or not. So we did an experiment. This is set up in our lab, where in essence we built like this kind of a tower here, this kind of a gate here, and on top of this gate, where the table is here, there's one tower, and you can see here on the right and on the left, as well as on the tower at two different heights, we have installed a set of sensors. This is one of the set of sensors. And in the sensors, we take RGB video so that we have like a reference information. We also take depth cameras. They offer some suggestion for Bahnhof Südkreuz. We also have Wi-Fi antennas. We have thermal imaging, like thermal imaging. We have millimeter wave radar. That's what many of the car companies are putting into the cars as distance sensors for parking, for instance. We have near-infrared webcams, which are like night vision webcams, and we have LiDARs. LiDARs is the technology that now many car makers are putting into the cars to have the cars understand their environment. And then we, going back to the bold claim, just use tech that humans don't understand. We did a big study with more than 200 individuals, collecting them in 3 sessions. We also presented this to them so that they understand what we're doing. So of course you can see normal visual lights, you can see depth camera images, you can see long wave infrared, so thermal imaging, night vision. This is how LiDAR looks like. This is how radar looks like. And then you would probably say, no, I'm not sure if that's going to work. But then we ran identification experiments on that, and the experiments show that even without us doing huge, amazing machine learning, we have pretty perfect recognition rates for different, well, for all of the different modalities: video, depth, near infrared, long wave infrared, LiDAR. Radar is a little bit worse. But then, as a matter of fact, we also heard about this situation that many of the telcos were saying we could do something like integrated sensing and communication, where they were saying we have antenna towers or cell towers for mobile communication. So we have essentially antennas in there that are already scanning their environment. So we could use this to scan like the environment of the cell towers, for instance, for counting people or whatever. And they were saying this is totally anonymous, right? I mean, obviously, Wi-Fi, we don't even know what these waves look like. And so we just did an experiment with Wi-Fi, which, as a matter of fact, is on a very similar range as 5G communication. And we showed that at 100% you recognize the people just by the way that they're reflecting radio waves, for instance, in Wi-Fi. So again, unfortunately, using tech that humans don't understand is a very common claim, but very often it doesn't really work. I'm gonna speed up a bit because I'm not fast enough yet. Maybe quickly take 3. We tried to figure out how identifying motions are, because there was this claim that the big Asian country with the video cameras could identify people based on gait, the way that people walk. And I found that very surprising. So we tried to figure out how we can measure that. So how can we actually measure if the person is identified by the gait? Because of course, if you think about the situation, the video camera would see video, but we didn't want to use the video because we can identify someone by their face is more or less obvious. So what we did is we only extracted certain points that reflect the movement of the people. And then people were talking earlier about k-anonymity. Then we thought, okay, so we try to make this data somehow k-anonymous by generalizing the data, suppressing data, normalizing the data, and so on, to see to which extent this would become anonymous. And for instance, here up on the top left, we see the raw data. We could coarsen the data in the sense that we reduced the amount of detail that we have. We could only take parts of the body, so for instance, only the legs or only the head. We could normalize the data in the sense that we normalize the speeds and the limb posture, and so the limb length and so on, so that then essentially all of the people should look more or less the same and walk at the same speed. And at some stage we even thought, okay, if we take away all of the absolute information, we only take the relative, only the movement, the way that certain parts of the body are moving, and let's see if this would actually prevent identification by machine learning. Turns out that none of this really works. If we only keep the head, then the recognition rate goes down to around about 60%. So you recognize only 6 out of 10 people, or in our case, I think it was maybe 120 out of 160 people. But for all of the other cases, the recognition rate remains comparatively high. So it's taking movement data, reducing it in some sense, and then hoping that it's going to be anonymous is not good. We can talk about federated learning maybe in the question and answer part. Many people are now saying that federated learning solved the problem because you could train machine learning models, for instance, in different hospitals and then merge them. Suffice to say, it does not work. There are a couple of papers showing that from the models, you can almost perfectly reconstruct the training data. So you don't really want to believe that federated learning is changing anything. And actually, as a matter of fact, but I'm going to be really quick here. At some stage, when we read the paper that I was mentioning earlier, we got so annoyed with this that we thought, okay, let's see if we can automatically invert the anonymization so that we could automatically reconstruct our original image with machine learning. And Julian, one of our PhD students, trained a model. No further details on the model. And then we used a lot of different commonly suggested anonymization approaches. Simple ones like removing pixel, Gaussian noise, eye masking, pixelization, and so on, but also more advanced approaches, like, for instance, using differential privacy. Forks is the mechanism I was talking about earlier, adversarial learning, and some others. And then we checked if we can reconstruct from the output what the model thought was the input, and you can see the reconstructed inputs here. Subsequently, we checked if the reconstructed input can be matched or identified, recognized as the original person again. And again, also I took out the slide here. Again, in some cases, it does not work super well. We can also argue if the utility is very high for such kind of data, but in almost all other cases, we can reconstruct the data perfectly, and then also recognition works perfectly. Noteworthy exemption is in painting. So some approaches now are essentially painting different personalities over the original personality. That can be very useful for machine learning. For instance, if you're collecting video for machine learning purposes, you could paint over the face or the person itself with an invented person, and that actually actively prevents recognition. And for that purpose, the utility is not even dropping. It's just like if you think about using Facebook or Instagram, then of course that wouldn't be a solution that is useful. All right, I got an indication that I'm running out of time, which I can understand very well. So maybe I was advertised as someone who would help you in your situation. I'm sorry that for the last 50 minutes I may have not done that. So then, of course, we can ask, is all lost? And can't we do scientific research with personally identifiable information? And I don't think so. I mean, fortunately, we have the GDPR. And as a matter of fact, what we can do is we can, first of all, assess the necessity of each of the data that we're collecting. If I'm doing a study using EEG or ECG, then I have to collect ECG. There's nothing I can do, but I can collect this specific information and ignore all the rest. So then I don't get poisoned by other kind of information, right? I can collect informed consent, and I guess that for our studies, we are doing a lot of studies where we're sharing data as well. Informed consent works actually quite well. And that can include sharing. So we've been publishing data sets where we collected informed consent, previously asking the people, is it okay for you if we share our data that we're collecting of you with other researchers? And people, if you ask them, for instance, in the study that I was presenting with a big gate of sensors, I think that maybe 4% of the people were not happy with that, so we took the data out. But for the rest, for them, it was fine. So then it's also fine that we share the data, of course. You can strip off anything not directly necessary for your study. So maybe you get smartwatch data, but you only need ECG data, throw away all of the rest. You can pseudonymize the data. I believe that, again, anonymization, I guess, is not going to work, but or very rarely going to work. But you can pseudonymize the data properly and try to reduce the risk of re-identification. And that can actually work comparatively well if you do it properly. And of course, you can separate the pseudonyms from the actual content, so that even if your content leaks, computers break and data leaks, so that even if the data leaks, you have the linking information somewhere else. All right, that brings me with skipping like 15 of my slides to my conclusion. I would like to repeat that anonymization is defined as preventing identification. I only talked about identity disclosure, right? I didn't talk about attribute disclosure today. But anonymization is defined as preventing identification. We see hundreds, thousands of papers that are suggesting certain anonymization approaches. And also when we talk to industry, there are plenty of people saying, oh, this data is anonymous, but it's my firm belief that most of them break under scrutiny if we actually test. What we can do, of course, is what we could do is we could improve the methodology of anonymization and testing and scrutinizing the methods. So we're developing also anonymization methods, and then we're honest with what we actually achieve. And then, of course, again, we can be honest with our users. So if we're collecting data about people, we can tell them the data is not anonymous, but we follow the GDPR and everything's going fine. Keep in mind, privacy harms do not require identification. Attribute disclosure can happen even if I'm not able to if I'm not able to identify you. And we're sitting just down the road, and we like to chat. We have a coffee machine. We drink a lot of coffee. So come talk to us if you have privacy questions. We're happy to help.